Hello, everyone. Welcome to our lecture on adversarial search in games. So, in the last lecture, we introduced the concept of adversarial search, and we went on to look at the minimax principle. Now, one thing that we mentioned was that when we are generating game trees, um, the size of the tree may be large. We did give an example of generating if we're to generate um, this tree from scratch, there will be so many. It would have so many branches, and it would be so complicated. Um, so in this lecture, we want to see how um, we can reduce the size of the tree, or how we can reduce the part of the tree that will be considered in the search tree. Um, Usually what we do as human beings away from computers, whenever we are making decisions, we do consider our options. Now, those options that are less promising, we avoid them. We consider the options that are more promising. Um, Imagine if you are, let's say, for example, trying to raise money maybe for your school fees, and you can approach maybe 5 people. Uh, Out of the 5 people, uh, you can approach, you are going to see who is more likely to assist you and who is less likely to assist you. And the one who is less likely to assist you, you will avoid them, or you will not approach them unless it fails with the other people who are more promising. So whenever we are making a decision, given a list of options that we have, we usually go for an option that is promising. So those options that are less promising, uh, we avoid them. Now, recall when we were discussing in class the memory complexity of depth first search, breadth first search. We did say um, some search options that we have may require more memory. Now, having a lot of, for example, states in memory, we said even the amount of time that will be required to process that will be large. Now, one thing that we like to do when we are playing games is we want to be able to, the game to move at an acceptable speed. We don't want, when I make a move, for example, here, I don't want the computer to take ages for it to make a decision to either go here or there. It should be within reasonable time. That could be maybe within a few seconds, so that the game keeps moving. Now, if we have so many branches, uh, that is going to take us a lot of time. So we ask ourselves, is there a way in which we can eliminate or avoid some of the branches that are less promising? Similar to the way we do it as human beings when when we're trying to make a choice, when we're trying to make a decision, we look at those options that are promising, and those which are less promising, we we avoid them. Okay, so we are going to introduce a way of cutting off the search, and that is by what is called alpha beta pruning. Okay, so what we are trying to do before I even talk about alpha beta pruning is this. If we look at an example here, this is a game tree that we populated, and we determined that the optimal move for this player should be this one. Now, imagine for us to get here, we had to look at all these nodes, some of them, some of whom were less promising, because we know that given here, they can get a 2, there they can get a 1, and there they can get a 1. Why go for these ones which are less promising? So now we are going to see how we can determine or how we can prune some of these that are less promising. Now, the concept of pruning, for those who've done any bit of any form of agriculture, gardening, for example, when you plant, when we plant, for example, tomatoes, okay, at some point, we're going to remove some of the branches which don't look so healthy. Now, why are we doing that? We are removing those branches that are not healthy, or we are pruning those branches that are not healthy, so that the other ones will have more space to grow. The idea of pruning, even with trees and others, those who are in agriculture, they will cut them, they will cut off some of the branches so that the other branches, the healthy branches, can grow. So that is a idea that we also want to use here. We want to eliminate those less promising branches so that the search process could be faster. So that's the idea. Now, in alpha beta pruning, which we'll discuss, which we are discussing actually, there are two um, there are two values that you need to keep in terms of the procedure. So first of all, we are going to use depth-first search. And as we do depth-first search, we need to keep two values in mind. The two values that we are going to keep is the alpha value. Now, the alpha value is the highest value seen so far on the maximizing level. Then there's a beta value, which is the lowest value seen so far on the minimizing level. So we are saying keep the highest value on the maximizing level, keep the lowest value on the minimizing level. And using these two values, we have this procedure. When you are trying to maximize, when the agent is trying to maximize its chance, it shouldn't expand any more sibling nodes once a node has been seen whose evaluation is lower than alpha. When minimizing, do not expand any sibling nodes once a node has been seen whose evaluation is greater than beta. Okay, so let's now look at an example to make sense out of this. So remember, we said the two values we want to keep track of is the beta value and the alpha value. The alpha value is the highest value seen so far on the maximizing. So when you are maximizing, so for example, here you are maximizing, there you are minimizing, you are maximizing. So when you are maximizing, keep track of the highest value seen so far at the maximizing level. Then when you are minimizing, um, uh, uh, keep the beta value, which is the lowest value which has been seen so far. Then the rule. The first rule is when you are maximizing, do not expand any more sibling nodes once a node has been seen whose evaluation is lower than alpha. So alpha, highest value seen so far on the maximizing level. Beta, lowest value seen so far on the minimizing level. So we'll keep these two rules. They are very important. So we're going to do depth first search. So using depth first search, now what we are trying to do is we are trying to see what what branches or what nodes we can prune from here based on their alpha and beta value. So here, we're going to look at the alpha value, and we said alpha value, this is the highest value we have seen so far. So with depth first search, remember, we are going to go with the leftmost branch until we get to the end. So when we get to the end, we have seen a 2. So at this point, we don't know what is here, because remember, depth first search will take us like this, where we have max, min, max. So each player is taking turns. Now, having taken turns, and now we are here. The next part, we look at what is the highest value we have seen so far on the maximizing level. So that is 2. Now, before we consider this one, we'll say, okay, the value of alpha that we are expecting something greater or equal to a 2. We haven't yet checked this side. So now that we have an idea, we expect a 2 or greater. Let's now consider the other child. So here we have the parent. So we look at the child. So when the parent is telling us to say, I'm expecting at least a 2. Worst case, I need to get a 2. Now, we look at the child. The child is 3, a negative 3. So now, since we have considered both this one and this one, we are now certain that the alpha value that we have seen, we are now certain that the alpha value that we have is a 2. Okay. Now, we are supposed to propagate this value upwards. Now, so far, we have only considered this branch. We have only considered this branch. So now we are going to try and see this side. Now, before we go this side, one thing that we know is here, this is a 2. It's the alpha value we have seen so far. So now at this level, this is a minimizing level. So on the minimizing level, we're saying keep track of the lowest value you have seen so far. So far, we've only seen this value. But because we haven't yet considered these children, here we are just going to put a provisional value where we say we are expecting beta to be less than or equal to 2. Less than or equal to 2. Now, we need to compare this parent with this child. Now, at this point, we have nothing here. At this point, we have nothing here to make the comparison. So we are going to now do our depth first search. Now we are going to, since we can't make this comparison, since we don't have anything here, we go down. So we take this route and that route. So when we go this way, we see an 8. That is before we even consider this branch. So remember, depth first search, we go to one branch, get to the end. That's when we go to the other children. So now that we are here, we've moved this way and we've come this way, we've seen an 8. So before we look at the other child node, we say, okay, when we come here, and because here we are trying to maximize, we are expecting an alpha value which is greater or equal to 8. So far, we haven't seen check to this side. So now we have these two values. We have a 2 and we have we have these two values. We have a 2 and we have an 8. So now let's go back to our alphabet rule. The procedure says when you are minimizing, do not expand any more child nodes. Do not expand any more child nodes once you see a value whose evaluation is greater than the beta level. So here, remember, at this level, we are trying to minimize. So meaning whatever option that we get, whatever the only promising nodes that are there are those which will guarantee us a lower value than the value of beta that we've currently seen. So we know that when we come here and we pick this option, and when it is 10 for the maximizing, they will try to get the highest possible value. And so far, because we have seen a value whose evaluation is greater than beta, which is an 8, then they are likely to pick that option. So the rule, when you are on the minimizing, do not expand any child nodes whose evaluation is greater than the value of beta. So we have only considered this one. We don't even need to check this one because we know that because of this evaluation, we know that when we are minimizing, we don't want to come this way because it is not promising. I hope that is okay. Let's continue. We've considered this path. So now we'll come and check this side. So we need to compare again this one with that one. Now, we don't have anything here. We don't have anything here. So we come back to our row. We now look at the payoff here. So when we move like this, when it's the maximizing 10, we expect a value greater than 3. So here we know that we expect a value greater or equal to 3. Now, we'll come back to our row. When minimizing the beta principle, when you are minimizing, do not expand any more children once you see a sibling whose evaluation is greater than that of beta. When you're minimizing, don't expand any more children once you see an evaluation whose value is greater than beta. So again, you don't need to check this side because you know that when it's time to minimize, if this 10 is taken, the opponent is guaranteed of at least a 3. So this is not promising. We ignore it. So far, we've eliminated this one. We've pruned these two because they are not promising. We know that once I come here and my opponent makes a move, they will get a payoff of 10, of at least an 8. So why should we go that way? We continue. So now we are back to maximizing. So when we are maximizing, we are saying keep a value of alpha. So the value of alpha that we have seen so far, so here we've only seen this estimate, a 2. So we are saying the value of alpha will be greater or equal to a 2. So now we'll come here. So do we have anything on maximizing, on minimizing? No. So we'll check. Do we have anything here? No. Then when we get here, we check here. This is a negative 2. Okay, so let me just clean. Okay. So we are saying when we come here and we come here, so we see a negative 2. So at this point, we are saying the value of alpha will be greater or minus 2. Now here, we don't have any value here, so we can't yet do the pruning. So we now also consider this one. So now we have a definite value. We've considered a -2 and a +1. So now we know that at this level, um, the value of alpha will be 1. The value of alpha will be 1. Okay. Now, we propagate this value upwards. Now, because we haven't yet considered what is here, so we are only going to put a provision, or we are going to put an estimate here, where we say we are expecting a value of beta to be less than or equal to 1. So now, at least we have an estimate here and we have an estimate there. Now, before we decide whether to continue expanding and considering these branches, these nodes, we go back to our procedure. In our procedure, we said, when you are expanding, when expanding, do not expand any child nodes once a value has been seen whose evaluation is lower than alpha. So when we look at here, we're expecting at least a 2. Then here we see an evaluation that is lower than alpha. We're saying don't expand any more child nodes because that's not a promising path. So whatever else that hasn't been considered, just ignore, prune from here. So anything below this, prune because it's not promising. So this one will not be considered. That node will not be considered. This node will not be considered. Why? They are not promising. So having done that, let's now come here. Do we have any value here, absolute or an estimate? No, we don't have. So we'll continue. So we'll now go, when we come this way, we'll go even that way. So again, all these are empty, so we'll continue. So when we come here, we see we have a value here which will propagate upwards. But before we consider this one, we'll just put an estimate to say the value of alpha will be greater or equal to 1. This is coming from this branch. After we've done this, the next part that we now consider is we say, okay, here I have an estimate, but I don't have anything here. So I can't propagate a value here yet until I check this side. So we check this side and we have a -1. So we've now considered both legs or both branches, so 1 and -1. So we are now sure that the value of alpha is a 1. The value of alpha is a 1. So now we can propagate something, we can have an estimate. Here we can only have a definite or an absolute value when we consider here the value that's here. Recall when we are doing a minimax principle, we are considering what is here and here, then we pick a value that is favorable, and that's what we put here. So here, we haven't yet come to this branch. We haven't yet come here. So since we just know we've only considered one part, we'll just say beta is less than or equal to a 1. Having done that, so now we consider, since at least we have an estimate here and we have an estimate there, let's go back to our alpha beta principle. We are saying when you are maximizing, do not expand any child node once an evaluation is seen whose value is lower than alpha. So when you are maximizing, so because we're trying to maximize, and here we've seen a child node whose evaluation is lower than our alpha, do not expand anymore. So these other children will be pruned. Why? Because we know that if we were to come here and it will be the turn of the minimizing agent or the opponent to choose. They will make sure we get a lower value. So the ones I've crossed out, these ones will not be considered in the search. And so what this effectively means is that these will not waste any memory because we'll have cut them off. So let me just clean all of it. Okay, so let me just clean it up so that we continue. So that is the idea of the alpha beta pruning. Okay, the alpha beta pruning. So quickly, let me just clean it up and then just close my annotations. Okay, so this is what we had worked on. So that is alpha beta pruning. So very quickly, let me share another example. I'll quickly pause and share another example. Okay, so here is another example that we have. So we just want to see alpha beta pruning, just another example of alpha beta pruning. So remember the two rules which we have talked about. We've said when you are maximizing, when you are on the when you're maximizing, don't expand any child nodes once an evaluation has seen that is lower than the alpha value. When you are minimizing, do not expand any children nodes once the value has been seen that is greater than the beta value. So we'll now just look at another worked example. So here we are trying to see which nodes are going to be avoided, which ones are going to be avoided, are going to be pruned in our search. So here, remember we said at the beginning we are going to go all the way down and then we'll keep track of the values that we have. So for a start, we do we do depth first search until we get to the end. So here we see a 4. So before we consider this other child, we just have an idea to say at the maximizing, since here we are trying to pick the maximum value, we expect at least a 4. That is what we have done here. Okay. Now, the next part, we'll say, okay, let's now consider this one. So since we have considered both this and this child, we now have a definite answer. We know that here, the maximum value seen so far is a 4. We are supposed to propagate this value upwards. So we are now on the minimizing level. Now, on the minimizing level, before we consider this, whatever value that will be here, we now just have an estimate. We say, okay, here at the most, since we are at the minimizing level, at the most, we shouldn't have anything greater than a 4. So that's why we have this value that is just an estimate. Now, as we go on, we say, okay, let's now consider this. Now, when we come here, we see a 6. So before we consider this child, the other, we know that worst case, here, since this is a maximizing level, we are saying we expect at least a 6. So for this level where we're trying to minimize, this is not so promising. So since we know that at this stage we want to pick the maximum level, the agent will be looking to get the maximum. It's pointless to bring them here since here we're trying to minimize. So this is not promising because the value here is greater than the beta value here. So this child is going to be pruned. So that has been pruned. Now we continue. So here we propagate this value. Since here we now have these two children. So we have a 4 and at least a 6. So we are now sure that the value of beta will be at least a 4. It will be a 4 here. So since we have considered this one and here, so we now have a 4 there. So we propagate this value up. So when we propagate this value up, because we haven't considered what is here and what is there, we'll just give an estimate where we say this will be at least a 4. Now we move on. Now, as we move on, we go this way. We get to a 2. When we get to a 2 here, since we don't have anything here, before we propagate, we say, let's look at this side as well. So when we consider a 2 and a 1 at the maximizing level, we now have a definite value of a 2 here. So we now have a definite value of a 2, and that's what we propagate. Now, on top here, when we have a 2 here, which will propagate here, we can only put an equal sign here when we have considered what value is here and what value is there. But because we haven't yet considered what value is there, here we'll just say great, since we are minimizing, we'll just say less than, it's supposed to be less than or equal to 2. That's the idea. So when we come here, we'll now say, we'll now use the alpha rule where we say, when you're maximizing, don't expand any child nodes once you see a node whose evaluation is lower than the alpha. So because 2 is lower than 4, we won't consider these remaining children because this is a less promising node, so less promising path. So that is what has happened here. This is what has happened here. Now, when we will now come to this path, so these ones, they haven't been expanded, they're highlighted ones. So when we come here, we are now moving here. So here we check, we don't have anything. So we come here. So we have a 5 and a 4. So here we've put greater or equal to because we haven't yet considered what is there. Then once we consider what is there, we are now sure that it's a 5 that is there. Then we take this one up. So when we take this one up, here we take this one up and we are putting an estimate less than or equal to 5. Then we come to our rule. When expanding, this is alpha at the alpha level. Don't expand any child nodes once you see an evaluation that is lower than the alpha. But lucky for us here, this is promising. It's greater than alpha. So meaning coming this way is promising for the agent. So we'll consider these other ones. Now, when we come here, we now go this way. We now come here. So we see a 7. A 7 is what we take up here. And again, we have an estimate. Since we are saying, if we were to come this side, we expect at least, at the maximum level, we expect at least a 7. Now, so we have this estimate, and on top, immediately on top is the minimizing level. So we now remember the beta rule, when it comes to beta pruning. When you are minimizing, don't expand any child nodes once an evaluation is seen that whose value is higher than the beta value. And that's what has happened here. So this child will not be expanded. So once we have these two, we even know that at least here we expect at least a 5. So these child nodes here will not be expanded because they are not promising. So that is alpha beta pruning. So this concludes our discussion on adversarial search. See you in the next session.